recording. Okay, we're recording. Let's start this slideshow. Let's also get a pointer. Let's have a red pointer. So, welcome. Let's talk about the golden ratio. Why? Because we can. That's a good enough reason, I guess. What is a ratio? It says a ratio helps you to compare quantities. It helps you to compare numbers. Some examples here. You can fit 15 of those smaller boxes in that large one. He looks twice the size of his older sister. You can fit 3 of those rulers in 2 meters of length. Or you can fill 3 of those buckets with 42 nuggets and then munch, munch, munch. You can fit 9 small houses on 6 of those trailers. Will be a bit weird, but hey. And that single bottle can contain exactly 1 liter of orange juice. In other words, it's all about numbers. It's all about like comparing the size of those numbers. It's all about like comparing quantities. That's what ratios are all about. Now, you can visualize a ratio, and here I've used a square, because a square has a width, and a square also has a height. And then, of course, for a square, they are the same. So how do you actually calculate a ratio? Well, simply by dividing one number over the other. So the ratio will be the width divided by the height. For the square, of course, the width equals the height. So this thing is also an h, because they're the same. And of course, h over h is always 1. So the ratio will be 1. In other words, if the two quantities are exactly the same, the ratio will be 1. If the two numbers you're comparing are exactly the same and you divide them over each other, then the ratio will always be exactly 1. What if those numbers are not the same? For example, here you can see a rectangle where one side is like 3 in length and the other one is 1 in length. If you divide those two, 3 over 1, you get like a ratio of 3. And the 3 says something like, okay, we know that like one number is 3 times the value of that other number. That's what we know. That's what we can read from this number. Okay? For the other rectangle here, 7, and it's like one length. The width is 7, and the other length, the height is 3. So you divide those two, 7 over 3, and the ratio will be 2 1/3. So it says something like, okay, we know that this height fits 2 1/3 times into this width. Yeah, so the width is 2 1/3 bigger than the height. Or you can say the height is 2 1/3 smaller than the width. It's the same thing. It just depends on like which one do you put here and which one I mean, you can write 7 over 3. You can also write 3 over 7. It just depends on like what's your standard, what's your agreement. Okay, here we make the agreement for now, and that we put the width on top. So it becomes easier to make statements on that ratio. Here, for example, you have like 5 units in width and 8 units in height. If you divide those two, 5 over 8, you get a number of less than 1. The previous numbers were greater than 1. This is actually smaller than 1. It also means that like, okay, we know by looking at this number, okay, that the top quantity will be less than the bottom quantity. So 5 is less than 8, of course. And that we can see that from the ratio, that's the whole thing. Yeah, so one side is 0.625 times bigger than the other, where in this scenario bigger actually means smaller, because of course the 5 here is smaller than the 8 there. That's all it says. Yeah. So you know, like we can actually find 3 ratios. The values can be exactly the same. Then the ratio will be 1. If the top value is smaller than the bottom value, the ratio will be less than 1. And if the top value is greater than the bottom value, the ratio will be greater than 1. Hello, Mr. Snail. How are you doing? Okay, some maths. If the ratio is 5 over 8, yeah, we can also write ratio as ratio divided by 1, because something divided by 1 is always something. 1 over 1 is 1, 100 over 1 is 100, and a trillion over 1 is also still a trillion. Now, then we can actually do a little trick, because if these two things are equal, so if this part is equal to that part, then that times that must also equal that times that. So we do that cross multiplication, yeah, of those values. So we know that ratio times 8 must equal 1 times 5. Or 8 ratios equals 5. Same thing. If you divide them both by 8, so 8 ratio divided by 8 equals 5 over 8, then the 8's cancel each other out here, and it simply says ratio equals 5 over 8 again. So of course we knew that already, because that's how we started over here. Nothing special there. Okay? Now, what's the golden ratio all about? Now, if you have a rectangle where one side is 1, yeah, and the other side is x minus 1, and we know that the sum of the two sides is x. In other words, 1 plus x minus 1. So the sum of the two sides, you will see, because the 1 cancels out with the minus 1, that the sum equals x. Now the question becomes like, can you find an x so that x over 1 equals exactly 1 divided by x minus 1? If you find that x, then you've got yourself the golden ratio. Yeah? So if you can find an x where x over 1 equals 1 over x minus 1, then you found yourself the golden ratio, and you go like, woohoo! So, what is x? And more importantly, what in the heck, what in the name of Sis do we do with it? Hello, Mr. Sis. That's a nice picture. Found it on Bing. Was a cool picture. So, more maths. So, if x over 1 equals 1 over x minus 1, then we know that x is known as the golden ratio. Now, we know we can actually do that cross multiplication. So, x times x minus 1 must equal 1 times 1. I've written that here. But x times x is x squared. X times minus 1 is minus x. And of course 1 times 1 equals 1. You bring the 1 to the other side, so the 1 becomes minus 1. And you get this equation that says x squared minus x minus 1 equals 0. Now, going back to high school, you've got two equations to solve this, to find the x's. I don't know what the plural for x is. The x's. Okay, yeah. You've got y equals ax squared plus bx plus c. And you've got how do you find those x's? x1 and x2 equals minus b plus or minus the square root of b squared minus 4ac over 2a. Now, what do we have here? X squared, so it actually says 1 times x squared. The 1 represents the a, it goes there. It says minus 1 times x, the minus 1 is the b. And finally this constant here, the minus 1, that's the c. So you find them here as well. So a equals 1, b equals minus 1, and c equals minus 1. You plug those numbers into this equation. You plug them in there, all of them, and you go oh, x 1 2 equals minus 1 plus or minus the square root of minus 1 squared minus 4 times 1 times minus 1 over 2 times 1. And you do your maths, and you find these are the two solutions. So x is either 1 plus the square root of 5 over 2, or x is 1 minus the square root of 5 over 2. Now, this thing here becomes a weird negative number, and I'm not sure what negative ratios mean, so we won't be looking at that one. But this is your golden ratio. That's the one this whole session is about. So why is that so special? Now, first of all, it's special because if you actually calculate the value for this number, so if you do it on your calculator and you type in 1 plus square root of 5 over 2, you get this number, 1.61803398875, and it goes on literally forever. It goes on forever, and there's no pattern in that number. It's an irrational number. It's not a rational number, it's an irrational number. It's a weird number, okay? It's a bit like pi and e and all that stuff. So actually, because it's so special, just like pi and e, we're going to call this one phi, named after the Greek called Phidias, who was an established sculptor, painter, and architect. You can find more on this person on Wikipedia if you look for Phidias. Okay, so imagine you now have a rectangle where one side is 1 unit, okay, and the other side is phi units. 1.61, blah, 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 blah. Now, why is this so special? Because if you look at like our original equation, yeah, x over 1 equals 1 over x minus 1. That equation only holds true if you plug in phi there, and if you plug in phi there. Yeah, so you get like 1.6 divided by 1 equals 1 over 1.6 minus 1. And you will see if you calculate this stuff, that's actually correct. But it won't work for any other value. For example, if you plug in the number 4 rather than phi, you get like 4 divided by 1 is 4, if I'm not mistaken. And that equals 1/3. That doesn't look right. 4 is not the same as 1/3, so this is definitely not okay. But this one is. So that makes it special. Hello, Mr. Owl, by the way. Hello, Mr. Owl. Now realize that the geometry, like a square or rectangle, is just to visualize stuff. I mean, in the end, like if your rectangle is small or big, as long as this is 1 and this is phi, this is 1 and this is phi, and this is 1 and this is phi, and this is 1 over here and this is phi over there. X times 1 and x times phi, it doesn't really matter. Same thing here, this is phi, this is 1, okay, same thing here, this is phi, this is 1, and finally a straight line, this will be phi, and this value over here represents 1. It's just a ratio, it's just like looking at like how big is 1 compared to the other. Yeah, so phi is like 1.61 blah 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 times 1. That's the idea. So we finally discovered the mystic phi. We know what it is, we know where it comes from. So it's time for a little exercise. You grab any credit card, bank card, freaking flyer card, loyalty card, well, any card that sits in your wallet. Get a ruler from somewhere, then measure the card's width and measure the card's height. Then divide both values by the height of the card. And what do you find? It's an interesting exercise. Go and do it. Alice would say, curiouser. No, curiouser and curiouser. I can't do a female voice. That's what Alice would say, okay? Yeah. Okay, to infinity and beyond and a wee bit further. So, see if you can find some more items that exhibit the golden ratio. And post them as comments under this video. Okay, as soon as 3 or more people have left their answers, then I'll make the next video in this weird math series, as it's fun to do. And I learned something from it myself as well. That's true. Okie dokie. Hey, some books, lots and lots of books on the golden ratio, and I'll also talk about Fibonacci at some stage, and a whole bunch of other numbers, of course. Like if you like these videos, I'm just playing with this stuff. I think it's fun. Okay, but lots of books you can read if you want to, and dig a little bit deeper into this special number. Okay, that's it for now. I'll hope to see you back in some other videos. Have fun, enjoy, bye bye.